Hello, it's the third lecture of week three. We're going to move into semiconductors today. So we've been talking about how electrons are kind of allocated in metallic bonding, right? And so the take-home message from the first two videos of this week have been electrons in metals are not localized. They're not fixed in a bond anywhere. They can move around, especially if we apply energy to them. And so today we're going to actually do that. We're going to look at what happens when we kind of manipulate where those electrons can go and all of that kind of stuff. And how do we do that? Okay, so today we're going to talk about semiconductors as a very kind of specific application, but one that gets used a ton. So there'll be an exercise in the course looking at maybe solar energy or light emitting diodes, those kinds of things, and we'll talk about that in this lecture and the next one. All right, let us begin. All right, so I want to look at group four, and the reason that we'll look at group four is um, going to be hopefully obvious here in a minute, right? So group four is carbon, silicon, germanium, and then as we go down, we have tin and lead, right, in the periodic table. So this is group four. Um, Carbon, of course, is a nonmetal. If you look at the molecular orbitals, there's a very large gap between the bonding and antibonding. Bonding and antibonding. Right? And so these are very poor conductors, right? In fact, you can use diamonds as insulators if you don't have any other use for diamonds. They're very good insulators. They do not conduct electricity at all, right? Of course, when you move down to the bottom of here and down here, tin and lead are metals. These have no gap between the conduction band and the valence band. And so tin and lead are very good conductors, great conductors, right? Because that's what metals do. Metals have high conductivity. Tin and lead are no exceptions to that. So, of course, now, why would I talk about this unless if I wanted to draw everybody's attention to silicon and germanium? These are kind of on this in-between area between uh, metals and non-metals. If we go back to the kind of the dividing line, silicon and germanium are right on that dividing line. And the answer is that these are kind of conductive. They're semiconductive. Right? They're semiconductors, meaning they can conduct electricity, but it takes work. Right? And so when we think about that, like what does that look like? And the answer is that in order for the electrons to get from the valence band here, valence band, up to the conduction band, right? In lead and tin, there's no gap here. Right? In carbon, this gap is much too large. In silicon and germanium, this band gap, the gap between the bands, is small enough that we can actually get the electrons can traverse it. They can go from being in the valence band to the conduction band, right? And so whenever we talk about semiconductors, we're going to talk about band gap quite a bit. And when we talk about band gap, right, this would be, right, the valence band, of course, is all the bonding orbitals, and the conduction band is all the antibonding orbitals. And remember that the electrons can move around once they get to the conduction band because they're no longer a part of any bonding, and so they're free to move. Right? So this is the important thing. So what are the criteria for semiconductors? We have two things. One, you have to have a full valence band. And so when we talk about a full valence band, there's a particular groups that are good, right? So first of all, group four, which is not an accident that I started with group four today, but group four elements are elemental semiconductors. And the reason for this is that they have pretty much half full right? Group 4 elements are halfway to the octet. So they have 4 uh, valence electrons out of 8. And so when they fill up the valence band and the conduction band, they fill the valence band, but they leave the conduction band empty, which is kind of the ideal situation for semiconductors, right? So full valence band, and I guess I should say empty conduction band as well. That's also an important criteria. Right? So group 4 elements are great for this because they have exactly half the electrons they need. So they put all their electrons in the valence band, they leave the conduction band empty. You can also mix and match, right? So you can also combine elements. We can combine elements, right, that result in the full valence band and empty conduction band. So right, so for example, if we take a group 3 plus a group 5 element and combine those together, overall, we're going to have 2 atoms. They're going to have 8 valence electrons between them. That's going to average out to 4 valence electrons per atom, and that will fill the valence band and keep the conduction band empty. Of course, you can also do group 2 and group 6. And those will also work to have a full valence band and an empty conduction band. So those 2 things are good. The second criteria that we have is that we need the right size band gap, right? We need a small band gap. And when we say small band gap, we mean 0 to 3.5 electron volts. So band gaps are always measured in electron volts. 0 to 3.5 is basically the criteria for semiconductors. Most of the really good semiconductors are going to be around 1, maybe into the 2 electron volt range, but technically anything in the 0 to 3.5 is there. How do we control the band gap? One thing that will control it is the atom size. So a larger sized atom means a smaller band gap, right? And we saw that kind of play out in our on the previous slide, right? When we have carbon is the smallest of the group 4 elements. That has a very large gap. In fact, it's no longer a conductor. Tin and lead are the largest, and so their the band gap gets smaller and smaller as we go down. Carbon is no good because the band gap is too small. Tin and lead are very poor semiconductors because, of course, their band gap ends up being too small, and so there's no longer any resistance to the conductivity. Silicon and germanium end up being right in the right size. So the larger the atom size gets, the smaller the band gap is. And then also, the farther apart on the periodic table they are, this ends up being a larger band gap. And so basically what we're seeing here is the farther apart they are, this is resulting in increased polarity. And if you get too far apart, you end up with dipoles, you end up with covalent bonds, that kind of thing, and you end up with a larger band gap. So this is if you're comparing, if you're looking at a group 3 element and a group 5 element, right? The group 3, group 5 combinations are generally going to have smaller band gaps than group 2, group 6 combinations because they are going to, they're closer, they're going to have less polar bonds. And so the less polarity you have, the smaller the band gap is going to be. Okay, so those are criteria. Those are the criteria for a semiconductor, right? We have to have a full valence band, an empty conduction band, and we have to also have the right size band gap. So we're gonna do some examples of this and practice kind of how does that actually work out when we look at these things. And then the next video is going to be about looking at those band gaps and how does that help us determine where the electrons are going and what do we do once we know where those electrons are going. So definitely I recommend you do the semiconductor activity now, and then we will jump into the fourth video of the week and the last video of the week, where we look at semiconductors and doping, and how do we affect the overall conductivity of semiconductors.